Hey everyone, and welcome to the Temporal Graph reading group. Today we have the pleasure of having Edwige Cipher. I don't know if I'm pronouncing that correctly. She is at the Institute of Science and Technology in Austria, Kloster Neuburg, Austria, and she's a postdoctoral researcher at ISTA in Vienna and will join the CNRS at Université Paris Dauphine in 2026 as a researcher. I don't know if I'm butchering that. Anyway, her PhD focused on differential privacy in fully decentralized learning, and she has published at leading venues such as NeurIPS, ICML, and AI Stats. She received the L'Oréal UNESCO for Women in Science Young Talents Award and is committed to promoting the role of women in science. That's super cool. Welcome and take it away with your great presentation.
Thank you, Victor, for the nice introduction. So yeah, I'm Edwige, and today I will present a work that I have done with Marc Damy, who is a PhD student both in Realil and Twente. And just disclaimer, is the first author of this work, and I am the one that have been pushing to make it more useful for people like me. And people like me are just looking for good data set for doing their own research, because what I am working on is machine learning most of the time. And for doing machine learning, you need a lot of data. So, like now ChatGPT is training on the whole internet, and you need also a lot of compute, and you would like to have a lot of heterogeneity in your data, because then when you deploy your model, you also have a lot of heterogeneity. So you need to cover all the possible cases. But on the other hand, you should not reveal too much about the data that you have been using for the training, because it can be illegal to do so. For instance, in Europe with the GDPR, but also it can be a reputational harm or even just a moral incentive to respect the privacy of your user. And the motivation to reconcile these two opposite goals that are we would like to use the data, and on the other hand, we would like to protect as much as we can the data. And is to reconcile that by using decentralization. And in most of my research, I'm really looking at how to see the impact of decentralization, both on the optimization side of the machine learning and on the privacy side. And when I talk about decentralized learning, what I mean is that most of the people, when they think about machine learning in general, they are talking about this centralized setting where even if the data, in fact, come from several users, they are centralized in one big data center that is then training the model. But you can remove this constraint of centralizing the data by doing federated learning, where you still have a central server, but you compute locally the gradient, so the model update that you need, and then only you recombine it. And you can even go further, and this is what I call decentralized learning or fully decentralized learning, meaning that you remove your central server, and then you just have peer-to-peer communication. And in this case, now you have a graph of communication that encodes which room you can exchange messages. Also, if you have any question at any time, just interrupt me and I will be really happy to answer the question. And just go ahead and don't raise your hand, because I cannot sit. So the question is, of course, I would like to have a graph of communication, but what are the possible graph of communication that actually make sense? Because now my model is the following. I have just this abstract graph, and I have algorithm to do different tasks. So if I want to just compute the average, it's super easy. I just need to do a ponderated average with my neighbor at each iteration, and I will converge after sometimes to the true mean of all the graph. And in fact, I can do much more complex tasks than computing the average, I can do any kind of minimizing global loss among all the node, and this is typically what you need if you want to train a global model on all the clients. And what happens when you do this kind of training is that the graph really matter. And this is some other work that I've done where you can see that you have a trade-off in the accuracy and the privacy you get depending on the graph topology. And here you can say that it's very sad because I'm doing privacy preserving machine learning techniques, but I don't have a good graph of communication. So I'm just looking at existing data set, and the only one I find is Facebook ego graph. So I'm taking this graph of communication where each age corresponds to 2 persons that are friends. I'm like, oh, that's nice because friends correspond to people that trust each other. So that's nice to make a connection between how much information you leak between these 2 persons and how much you are related to this person. But on the other hand, I'm like, if I am on Facebook, I have very low privacy expectation anyway. So is it useful to derive this result if I only can test it on example where people don't care that much about privacy? And that was the motivation to do this work on Fedivertex that I'm presenting today. I was looking for a very nice application, a real convincing application for combining decentralization and privacy. And I was quite lucky because there is a natural application is to look not at this mainstream social network, but alternative one where people are a bit more careful about trustworthiness in general. And I don't know if you are familiar with the Fediverse, but it's several social network of software that share the same idea that you don't have one central server, but you have a lot of different instances, and each instance come with the person that is hosting this instance that can decide what are the rules on this instance, what is the policy, and each instance has their own user. But they are not isolated, meaning that they can communicate with other instances. And so that's why the name Fediverse comes from the portmanteau of federation plus universe. And I put also the small logo that is this asterism, so you have like many stars together. And it's the idea that you have a very nice ensemble that is just done by these several entities that keep the power to take good decision. And there is a unity on all this software. It's behind, they are all using the same protocol to exchange the messages with, in terms of posting, sending, receiving notification. And so it means that we have some unity, and in practice for us, what this means is that we were able to collect the data with similar practice and to make something that is unified, despite the fact that we are looking at very different networks. And more precisely, you have we focused on seven social networks in this work. Why did we choose these 7 social network? It was based on several criteria. It was first we decided that we wanted networks that are big enough to have enough data to collect and to have enough signal to make it interesting. Then there was the question on, is it possible to actually crawl it? And also within this subset, we just tried to be as diverse as possible. So here you can see that we have Lemmy that can be seen as an alternative to Reddit. So you have PeerTube that is an alternative to YouTube, and Bookworm that is basically an alternative to Goodreads. And you can see that, so what we do in practice is to look at the graph of the instances. So here I report the number of instances, and you can think about it as the number of nodes in the graph. And you can see that each instances can have a lot of users. And you can think about the number of users as being a proxy for how important is that node. So you have some weighting on the node if you want to. And the biggest application is what we call this micro-blogging social network. So, like Mastodon, you are posting tweets, and that's an alternative to Twitter. Then you have Pleroma, Friendica, that are more or less alternative to Facebook. And you have Miski, that is much more popular in Asian country, whereas the other social network are a bit more European or American, but I will go a bit more deep on that. So how did we collect that data? We coded a crawler that we also make public. So meaning that what I'm presenting today is what we have collected over now 8 months of data collection. But if you want to crawl again this social network with a different decision in terms of what you want to keep, what you want, how you want to space the different collection, it would be way easier to reproduce because you can just reuse the same crawler. And we tried it because the motivation was really to make the dataset as trustworthy as possible. We decided to be very cautious on what we put in the crawler. And also we made a huge work with all the legal team of the universities to ensure that it was GDPR compliant and everything compliant. So in particular, we respect the robots text file, but we also respect the hashtag nobots. So even if people do not configure correctly the robots file, we still respect the intention. And because all these instances, most of them are hosted by individual that don't have very big resources to host it. So we make sure that we are not dosing them by crawling. So we limit the number of queries, and we try to balance the load as much as possible. There was also the question what we want to include in the dataset, because that's also true that this kind of alternative social network can also be of interest of some people that are using it for harmful content. And so we decided to just follow the Fediverse observer list that tried to maintain a list of okay instances. And so now, if you want to download the dataset today, we have done 1 crawl per week, and we have now more than 700 graphs online because each week we collect 13 different graphs. And the goal is really to continue to have at least 1 year of data to follow the evolution through time. And just some of the graphs are a bit more sensitive because they depend on the interaction between users. And so to respect the decision of the legal team of the university, we limited the crawling of this part to 6 months.
I have a quick question just for the crawling part. So some of the crawls that you're doing, are they like reproducible? Like, so, if I want to crawl 2 months ago, is that something? Or if you, for instance, your crawler crashes or the university cluster is dead for 1 month, then we just lose that snapshot? Or how are you dealing with that?
So yeah, that was a concern for us. How it is done in practice is just you have some error if the crawling is not behaving correctly. But in fact, I think that because we have this very small impact on the instances, we have never encountered a problem during crawling. So just it happens that we do have all the graph because we were never banned so far, so everything is fine. And then, of course, we have some backup, but if we don't do the crawling, there is not a backup of the Fediverse. So if we don't do the crawling, then we cannot have this snapshot. But
Okay.
just for now, we managed to do it without interruptions so far. So you really have the 8 months period without interruption.
Okay, thank you.
But yeah, that's the question. Like, we don't know what would happen if you reuse the crawler with a very different frequency. Like, if you want to crawl every hours, I cannot promise that it would work as well, you know. That we also choose that because we saw that it was a good balance between, you know, how fast this network are evolving. So yeah, in terms of graph, we have a lot of different graphs. So there is this default graph, I would say, that corresponds to the federation that we call federation. And we just put edges between instances if there is an interaction between them, meaning that you can see some content from one instance in the other instance. And we have this graph for all the social network that I presented, except for PeerTube, because in the PeerTube, instead we have the follow graph, because it's asymmetric. It's just one instance that decides to follow another one, but by default it's not reciprocal, which kind of makes sense because the content is video, so it's very big. So you cannot be sure that a small instance could be followed by a very big instance. Then what we do to have a bit more the interaction between the user, we have this active user graph that is constructed in the following way. We take the 10,000 most recent active user, so the user that actually connected to the server. And for each of them, we look at who they follow on other instances and also on their own instances. And every time we find one follow relationship, we increase the weight of the edge by 1. So it means that now you have a weighted graph that can be directed, and the weight really corresponds on how much content is seen on the other instance from a given instance. And we have that for all the micro-blogging platform. And this is a very sparse graph. I will show a bit more later. For the Lemmy, it's nearly the same. It just in terms of publication, because you have to keep in mind that it's a setting that is very close to Reddit, so people do this thread with post. So it was more appropriate to collect the data. And for Lemmy, we do something that is a bit less sparse. It's saying that we will create an edge not only if you talk on V, but if two users interact on a platform, even if it's a third entity, we create an edge between the two instances. So now it's an undirected graph because you know, the two users are symmetric. We just do not report who was the third instance in this case. So you can also see that a bit like a one-up of the intra-instance graph. So this gives you a very different graph. So here I just put the degree distribution of 2 Lemmy graph and 2 Mastodon graph. And you can see that for the federation on Lemmy, you have something that is quite sparse, whereas the Mastodon graph is much more dense. And for the intra instance, you have something that is also with a power law decay that is quite fast, whereas you have something that is a bit more smoother on Mastodon. Also, keep in mind that the two graphs have not at all the same size. Mastodon has a very good name. It's really the biggest graph in our data set. So yeah, you can choose what kind of graph you want depending on this feature. And just to compare with the existing baseline, so I have tried to report all the graphs that I used before in my research. So you have the Facebook ego graph, similarly the Twitter ego graph. You have the GitHub graph that is come from who share which repository. So, to have like this a bit reputation system. And you have also this existing Wikipedia vote to choose who are the moderator. And you can see that in comparison, the graphs that we collected, you have less this exponential decay. So you have less diagonal on the figure. And we believe that this makes sense because in comparison on all these alternative social network, you don't have that much incentive to go on you don't have this winner take it all approach. You don't try to get as big as possible. And also you don't have new link recommendation because that's something that is known that by you have a very fast thread closure on social media because just you get recommended in your friends and then you accept them and then you close the triangle. Whereas on this platform you don't have that, and which means that you don't see appear this scaling law in the same way. So that also is interesting if you want to have some different behavior on the experiment. So one of the applications of the dataset is to use it for community detection. And so we tried to include some possible label. A label that seems reasonable was to use the language. So each instance can declare what is the official language of the instance. Some of them do not declare it, but so that's the unknown. But you could also choose to post-process it a bit more and to just go on the instance and automatically detect what is the language. We decided that it was not that useful to do that in the sense that by default you can also just assume that it's English if you want to, and some instance also report several language, which can also be interesting because then you have multi-level stuff. And you can see that depending on the social network, you don't have the same distribution at all. And you can have something more balanced or less balanced. And you can see also on MISKI, which is the bottom, the bottom right figure. Sorry, I forgot to put the label, but on the bottom right, it's the MISKI distribution, and you can see that it's not the same language because it's much more Asian-related language. We also include in the dataset an automatic way to load the label for PeerTube on the topic. So on PeerTube, you can say what is the kind of topic of video that you have on a given instance. Like, is it about dance? Is it about food, or so on and so on? And so you can also use that as a label. So when I say use it as a label, it's just that you can directly load this label. We also have for each instance much more parameter that you could, if you want, process to make them label, but we haven't done that. And just to give an example, what does it look like? So here, this is a snapshot of the peer-tube graph and the MISKI graph, and you can the color correspond to the language, and you see that the distribution is not at all the same. On the MISKI, you really have the Japanese instances that take most of the instances, whereas on PeerTube it's a bit more European, and you have something that is more distributed. And for both of these graphs, you can also go online on this link and directly interact with it and open the name and what is the language, what is the number of users, and so on and so on. So we have this interactive version. And yeah, and just to finish on this dataset presentation, we also just run some baseline for community detection without label. So just if you want to compare, the baseline are already there, but we did not try to optimize them. So I guess that if you use clever algorithm, you can easily beat this baseline.
Just to understand this table here, is that for trying to predict what language or what?
Yeah. So here some of at least one of them is without. So here we report different metrics, and I don't remember which one, but which one. There is one that is just how well clustered are the community, and it's
Okay.
not label dependent. And we also report label dependent. If it's label dependent, then we try to predict the language.
Right. Okay. Thank you.
So then when we started to collect the data, after a while, we were like, okay, are we doing it right? Because this is what we get for the temporal evolution. So here, what I'm reporting is on the two first column, you have the difference between the number of ages at time t and time t minus 1. So between the current week and the week before. And you can see that it is changing a lot, which is cool, but it's not very stable. And in practice, what we do for computing the difference of ages is that we fix the node to be equal, because otherwise, it's not very well defined. And when we also look at the evolution of the number of nodes, you can see that it's really changing over time. So when we saw that, we were a bit suspicious and wondered whether or not it was a crawling problem, or if it's really that some node choose to unfollow some other and sometimes disappear and appear again. And it appears that so our calling was quite reproducible, so it was not an issue from our side. It's really some instances are appearing and disappearing again and reappearing, and sometimes also people on purpose choose to unfollow some other instances. And this is a phenomenon that have been reported in some other more sociology papers and machine learning paper. So it was a behavior that was known. Sometimes there was some political behavior, meaning choosing to all unfollow a given instance that is not seen as a good instances for the community in general. So you really have actual signal in it. And also in terms of node disappearance, it can be explained by the fact that most of the instances are not hosted by big company, but by individual on their home computer and this kind of stuff. So it means that they're really less stable, and they can also give up on hosting an instance at a given time. And so what we did to test a bit more this hypothesis, that here what you can see on each of these graphs is that in black, you have the difference between 1 week and the next week. And then the darker curve is after 2 weeks, then after 4 weeks, and then until the end of the data collection. And so you can see that sometimes some edges can disappear and then appear again, but you really have the same patterns, whether you look at 1 week and then the other, or do the difference between several weeks or not, and you do have edges that disappear forever. So there is a mix between this, small interruption between edges and definite separation between two groups. And how big is the difference? It really depends on the instances and of the social network that we study. So here you can see, for instance, on Friendica, you can see that actually you do have a bit higher variance just if you look at 1 week, but after 2 weeks, it's mainly done forever in most of the cases. And on the Lemmy graph, you can see that if I look at the federation graph, it's really only true disappearance that is reported. But now if I look at the cross instance, if you remember how it works, it is just based on who is communicating with whom, the last 10K user with whom they decided on which instance to interact. And here it's kind of makes sense that it changed over time because just people can follow some trend and so on. So just to say it's the real signal, it does capture the evolution of the graph. And in the paper, you can find all this figure for all the graph over time, and you can see the different behavior. So when we observe that, we believe that maybe it could also be an interesting prediction task, meaning that usually when you have this temporal graph, what you can do is to do edge prediction, meaning that you want to find the edges that correspond to the common nodes between the two iterations that were not present at time t, but are now in the graph at t prime. But what you could do instead is also try to predict which edges were there at time t, but are not there anymore at time t prime. And what is funny is that, of course, if your graph is sparse, the edges that you can delete lie in a very small set as well. So we were hoping to have a bit less variance on this task. But of course, we don't know how to solve this task by default. So in the paper, we did some very naive baseline that consists in saying that predicting that the edge is appearing is the opposite to predicting that the edge is disappearing. So let's take the same measurement. So you have this matrix such as Adama-Kadar matrix or common neighbors, and instead of taking the highest rank, let's take the lower rank. And you can see that that it is better than random in most of the cases. So doing that allows to capture a bit some signal, but I guess someone could think about better methods and maybe find a bit more signal with better method. And I think that would be great because one of the difficulty also in this defederation task is that we have seen that the number of nodes on a lot of social network of the Fediverse is decreasing over time, which can be explained by the fact that people go on the biggest instances and some instances just die out. And that's not good for the decentralization. And so maybe if people were able to predict a bit what are the instances at risk, maybe it would be also possible to help them to stay healthy and stay online in the future. Okay, so I started my talk by saying that I was motivated by my own research on machine learning in decentralized setting. So did I fulfill my goal? And I would say, yes, I managed to use this data set for my own research because it's really easy to do so. So basically, if you want to use it, you can directly install it with pip. So just pip install Fedivertex. And then when you want to use a graph, you just download it directly with this graph loader. So you just declare this loader, and then you get the graph. You just have to specify which software you would like, which kind of graph, and what time you would like. So here I put an example with the index, but you can also just specify the date of the graph. And if you don't remember which data are available, we do have some util function on what are the possible graph, what are the possible date, what are everything, so you can really autocomplete and do it easily. You can also directly choose to only keep the biggest connects component. So in like 3 lines, you have the graph that is ready to be processed, because now with this code, G is now a NetworkX graph instance. And also, that was a requirement of the NeurIPS mission. We use Croissant. And what does it do in practice? The first time that you are using the graph is loaded and then stored in cache. So then you don't have to download it again when you do it later. And it's really easy if there is any update on the dataset as well. So everything is working out of the box, even if you don't know how to do some call or more advanced technique. And what we did for the paper is I just reproduced some of the old experiments that I did for another paper on other graph. And I think that was kind of interesting because on the top, on the left figure, you can see that you really need to know the graph topology, because the communicability is something that a metric you can compute on graph. And it happens that it's really related to the privacy loss of the algorithm that I studied. And you can see that by taking this bookworm, you also have the same patterns. And similarly, on this example with Lemmy, you can see that once again, we recover the same structure between the privacy loss and the cat's centrality. And on the right, you have the dark blue curves that correspond to the curve done with Mastodont. And you can see that this curve is much much worse than the one that was done on synthetic graph, because you can compare with the green curve that was done on a geometric graph, and it's much harder to converge, to improve the accuracy with the true Mastodon graph. So it means that by using this real graph, I'm also able to push a bit more my methods and to see that we can still make progress. This is another example with another paper that is currently preprint. So this is also proving that the third person managed to use our dataset, so it should not be hard at all. And here again, it was on the PeerTube graph, and it worked, and it was interesting because it allows us to see interesting pattern between each of the methods that did not perform at the same scale. So in the conclusion, you can use the dataset for what it was meant for, meaning that if you take your decentralized learning experiment, you can run it very easily on this dataset. And just, of course, to conclude, please use our dataset. What does that mean? Use our crawler if you want something with a different frequency, or if you want to focus on one social network with more data point or a given or more data, because here we really focus on just the instances properties, but the crawler needs to access a lot of information for doing so. So you could also decide to collect specific statistics on the user if you need them. If you want just to have a nice graph topology evolving with time, you can just directly use the pip package and it works out of the box. If you need something in between, you can also just look at the several Jupyter notebook we put on Kaggle, where you have all the detailed analysis with a lot of other statistics about the graph. And you can also just look at the paper if you want to know a bit more also about how we did all this work and the comparison with existing methods. And just to conclude, what we were a bit sad about when creating this data is that a lot of edges and nodes are also disappearing. So it's not clear whether the Fediverse will continue to be healthy or is it struggling. Sometimes we joked during this work that if Fediverse is dying, then at least Fedivertex will be a nice post-mortem. But in the meantime, the fact that we have this defederation, I believe that it can also be a nice task to know if you understand the temporal dynamic of the graph or not. And I would be really interested to see if there are actually good methods to predict this deletion. And as last motivation behind this work was to say, now that we have this real-world data set, it's also the perfect benchmark to develop some tools that could be useful for trustworthy machine learning applications, such as just blocking spam on the Fediverse. And that's it. So thanks a lot for your attention, and I will be super happy to take your questions.
Thank you. I can see there's a lot of clap emojis. That's great. Do anyone have any questions that they want to either write in chat or unmute themselves? Otherwise, I can ask some questions to begin with. So I have one question, and if you can jump back a few slides to the table with the add and deletion task.
Yeah.
And this is such a cool Beamer template. I love this. I like that you can just click here and anyway. So if you go to the so you have let's stay at this slide. Basically, you have two tasks, right? That you try to predict future edges, like if they're created or if they're not created, and you try to, for given edges, you try to predict if they're deleted or not deleted, right?
Exactly.
Okay. So for the edges that, like for the edge prediction task, right? Then you have some true positives, which are edges that actually exist in the future, and you have some negatives that are randomly sampled non-appearing edges, or how?
Yeah, that's exactly that. So actually edge prediction is something that is kind of a mainstream task, I would say. At least I find a lot of references and include them. And we benchmark it in the usual way, that is, for each possible edge, you compute your metric, and then you take all the highest ranking. And for this set of the, like, let's say, I don't remember, so here it was around the highest 1000 ranking, we look at which one are actually added.
Okay, cool. because I feel like there's like for this edge prediction task, there's many ways of how people, sample the negatives or compute all of the possible edges. But yeah,
Yeah. So, and I think that's nice in the edge deletion that the set is much smaller.
yeah. What is the class balance for the edge deletion task like? Because I guess the majority of the edges won't be deleted, or did you have
Yeah.
some?
So yeah, it's very unbalanced. It depends on the graph. So I'm not able to say
Yeah.
like that. I could look at, but I don't know. But also there was this question. So here also a limitation is that we really did it. What we did is that we just cut the time in 3 big periods, and then we look at the difference between the beginning and the end of the period for each of these 3 periods.
Hmm.
And we did that because we could do it exactly. It was working for these 3 graphs at the same time, so it was kind of unifying the stuff. But you can see that on Mastodon, you have much more activity than on the MISCI active user activity.
Cool.
So if you want to target one specific graph, I guess that you could do something a bit more precise. Also, we choose. I wanted to be sure that my plus minus makes sense, so I decided that I didn't want it to have overlap between the periods. But I know that you can do some more clever stuff if you want to have overlapping periods.
Cool. I think there's one question in the chat. I can read it out loud if you like. It
Yes.
says, Brillian asks, interesting. Do you think that the defederation prediction task can be applied to the other than the decentralized systems?
I really don't know because like I never heard about this task before, and and the thing is, the only references that I found was really related to the Fediverse because you have this because moderator of each instance usually they really want to make decision. They are not passive user. If you take a usual social network, I believe that the behavior of removing someone from your friend is really not something that happen a lot. Whereas here it's something that has been reported and also like as as a choice, as a policy, to avoid too much federation. You should not link yourself too much with other people, so you keep the defederation process. But maybe there are other example of this behavior. I just don't know about it.
Interesting. I also have a question regarding like because I have many questions. We can go on, but I think like do you have any idea because now that if you jump back to the slides where you have the different data sets like you have Mastodon and you have this Japanese
Yeah.
MISCI, exactly all of these. Um, do you have any gut feeling? Because, and now maybe it's my stereotypes, but I have some stereotypes like you have the whole population, you have the population of the people that use Facebook or something like that. And then maybe you have some other types of users that go on stuff like Mastodon or something. Do you have anything like that can speak to like how representative or what is the distribution of your data compared to like other, if you compare Mastodon to something like Twitter?
So that's an interesting question. What
Thank
we
you.
were really looking for, and we didn't manage to observe it so far, is that it has been reported in the past that where there was some crazy policy on Twitter, people were creating new account on Mastodon.
Hmm.
But these peaks were reported before we had the legal authorization to start the crawling, because like we took 1 year to be able to actually crawl this data. And there was some other, I mean, basically, there was, we have been crawling at the same time that there was Grok that was deployed on Twitter and everything, but we have not seen this big rewards that were reported in the past. So our hypothesis is that people that decided that it was too much already left before we arrived. But that would be super nice to observe something like that. What we can also do, we haven't done it, but it's possible to do it with our crawler as well, is that all these social network, they are based on the same activity pub protocol, which means that basically you can share a Mastodon content on a Pleroma instance. So you have some interaction between these 7 social networks. And it's possible to report that. We haven't done it because I can't see really the application, and it would have been much more complex because then you have just one big graph, but that could be interesting. There is one paper that tried to do that, but the data is not available, and I think the findings are a bit not that clear, but that could be interesting. For now, what you can see easily is the language distribution, and also I haven't put it, but you can find the map of all the instances. You can know where are the people. Also, another way, and I believe that would be the most interesting to compare it, you could also crawl on our dataset. We already report the name of the instances, and usually the name are really explicit, so you know what the instance is about. And this, I believe, you could do some NLP to analyze that.
Cool. Any other questions from the audience? Maybe I have one last one. If you have the time, we're also 1 minute overdue. But like, how was because I've also have some familiarity with creating Python packages yourself. Like, when did you start this? Were you like in the beginning of the project, now we're gonna create a Python package, or was it more towards the end, like now we have all of this and we need to wrap it up in a Python package? And what did you think of that? Was it did you learn something?
I think that it was, I think we decided to do the Python package even before having the first bit of data. Because the motivation was really, I want to do my research with good graphs that correspond to real instances of possible people that would be interested by trustworthy machine learning. And this is just the best example I can think of. So, but I don't want to have very complex code that cannot be reproduced. I really want that when I share my code of my machine learning paper, people can just install it and rerun it. So that was a huge motivation, and that's why we really design everything also to be able to do that. I think the biggest issue was being compatible with Croissant, because this was imposed by the fact that we wanted to submit to NeurIPS, and I feel like this tool is not very mature in comparison. So basically, that was me sending email to Mark saying, "Oh, it's not working. Do you understand this error?" But we figure it out.
That's so cool. That's so cool. I feel like it's very rare, or like maybe that's just me, but that you actually have like Python packages coming out of research, and I think it is kind of important for reproduction, right? That so that's
the motivation, and we really look forward like keeping it updated. And for sure, like I presented, I show you an example of a paper that I just submitted using also this package, and I'm really planning to continue to use it and to try to make it to expand it. So yeah.
Nice. Good. I think that was my final question. So unless there's any other questions from the audience, I feel like we should give Edwige a big hand of applause and say thank you so much for joining the Temporal Graph Reading Group. I think also worth mentioning is that this week we did it 1 hour early for the people in not on winter time, or 1 hour early for the people on winter time. But for the people that shift in the US, no, I completely butchered that. We'll stick to the 5 p.m. European next week again. So thank you so much, and have a great day, everyone.
Thank you.
Thank you very much.